selecting the right technology for different dairy processing needs. Hello everyone, and welcome back to our channel mootechie. It's great to have you with us for another class in our dairy engineering series. This is class 8 of unit 4, where we will now focus on a very important application of sterilization, the production of UHT milk and the aseptic processing plants that make it possible. We begin with UHT milk. UHT stands for ultra high temperature processing. The principle combines a very rapid heating of milk to a temperature between 135 and 150 degrees Celsius, typically around 140 degrees Celsius, followed by an equally rapid cooling down to about 25 degrees Celsius. This treated milk is then packaged aseptically in bricks, bottles, or bags. A wide variety of products are commonly processed using UHT technology. This includes fresh and recombined liquid milk, concentrated milk, dairy creams, flavored milk drinks, and fermented products like yogurt and buttermilk. The list also extends to whey-based drinks, ice cream mix, desserts like custards, protein drinks, soy drinks, baby foods, fruit and vegetable juices, tea and coffee beverages, vegetable fat-based toppings, soups, sauces, purees, dressings, and nutritional solutions. The overall aseptic process flow involves several key stages. It starts with the product, which undergoes HTST or UHT processing. The product is then held in a cooling tank before being sent to the packaging line. The packaging material itself is sterilized, then the product is filled into it, and the package is sealed. Finally, the sterile product moves to storage and distribution. UHT plants can be categorized by their heating energy source and method. The two main heating methods are indirect heating and direct heating. Indirect heating uses a physical barrier to transfer heat and can be powered by steam or electricity, using conductive heating through plates, tubes, or scraped surfaces. Direct heating brings steam into direct contact with the product and is subdivided into injection, where steam is injected into the milk, and infusion, where milk is infused into steam. Let's first explore indirect heating systems. These are defined by the form of the heat transfer surface, which can be plate heat exchangers, tubular heat exchangers, or scraped surface heat exchangers. Plate heat exchangers for UHT processing must withstand much higher temperatures and internal pressures than those used for pasteurization. They operate at 135 to 150 degrees Celsius. To prevent the product from boiling at these high temperatures, a back pressure must be maintained. For example, at 135 degrees Celsius, a back pressure of about 2 bars is needed, and at 150 degrees Celsius, it needs to be about 3.75 bars. A typical UHT process using a plate heat exchanger includes a balance tank, a feed pump, the plate heat exchanger itself for heating and cooling, a holding tube to ensure the required time at temperature, an aseptic tank, and finally, aseptic filling. Another type is tubular heat exchangers. These come in types like the double pipe heat exchanger, which is a 2-tube system, and the triple tube system. A concentric tubes heat exchanger can be a simple 2-tube system for heating and cooling, often with a regenerative section to save energy. The triple tube system is used for the final stage of heating with steam. A typical concentric tube indirect UHT plant includes a balance tank, a centrifugal pump, a regenerative heater, a homogenizer, another regenerator, a steam heated section, a holding tube, a water-cooled section, a back pressure valve, a cooler, and a restrictor. A detailed diagram of an indirect UHT system, based on tubular heat exchangers, shows components like a balance tank, feed pump, tubular heat exchangers for preheating, heating, and cooling, a non-aseptic homogenizer, an aseptic tank, an aseptic filler, and a CIP system. The flow involves steam for heating, cooling water, and a diverted flow for milk that doesn't meet sterility standards. Next, we have scraped surface heat exchangers. These consist of a jacketed cylinder. The product passes along the cylinder, while the jacket contains the heating or cooling medium. A shaft with scraper blades rotates inside. The blades improve turbulence for better heat transfer and reduce fouling on the cylinder wall. The design shows the product and heating medium flowing. The key parts are the cylinder, the rotor, and the blades. Another diagram illustrates how the product flows in, and the rotating shaft with scrapers moves it through, while the heating or cooling medium flows around the jacketed cylinder in modules. A UHT process using a scraped surface heat exchanger includes a product tank, a positive feed pump, scraped surface heat exchangers for heating, a holding tube, more scraped surface units for cooling, and another positive pump. The system uses steam, cooling water, and has a diverted flow line. Now let's turn to direct heating systems. Here the heating medium, which is steam, is brought into direct contact with the product. In a typical flow, milk is first preheated by regeneration, then further heated by direct steam injection or infusion. It passes through a holding section, then into a vacuum vessel where flash cooling occurs, removing the water added by the steam. It may then go to a homogenizer before aseptic filling. In direct systems, the product is first heated to 80 to 85 degrees Celsius indirectly. Then, direct injection or infusion of steam raises it rapidly to the sterilizing temperature of 140 to 150 degrees Celsius. This causes dilution because the condensing steam adds water. After holding, expansion cooling in a vacuum vessel removes this added water. A temperature time graph shows the product being preheated, then experiencing a very sharp temperature rise during steam injection or infusion. It holds for 2 to 6 seconds, then undergoes a sharp cooling drop as it sprays into a vacuum chamber, ending just 1 to 3 degrees above the preheat temperature. Direct heating systems are divided into two types, the injection system and the infusion system. The injection system is a steam into product type. Steam at a higher pressure is injected into the product stream through a nozzle and condenses, instantly transferring heat. The steam injector is the heart of this system. The rapid condensation of steam reduces the effective holding time. This rapid condensation is achieved by introducing steam as small bubbles or a thin sheet. Maintaining sufficient back pressure in the liquid at the injector is critical to prevent boiling. There are different steam injector designs. In design A, the product flows through a venturi tube. Steam is supplied through surrounding tubes and enters the product via small orifices, creating small bubbles for rapid condensation. In design B, steam is injected at a sharp angle across the flow of the product, which is shaped into a thin, inwardly directed cone. This leads to rapid mixing and condensation. In design C, the product passes through a venturi. Steam is injected as a thin annulus in the expansion section, where pressure is rising. A second venturi section causes further pressure changes, encouraging condensation. A complete UHT process using direct steam injection with a plate heat exchanger includes a balance tank, milk pump, plate heat exchanger for preheating, a steam injection head, a holding tube, a vacuum vessel with a vacuum pump, a centrifugal pump, an aseptic homogenizer, an aseptic tank, and aseptic filling. An injection type UHT plant diagram shows a balance tank, heating section, heat exchanger, steam injector, expansion cooling vessel, condenser and homogenizer, with flows for water, steam and vacuum. The other direct method is the infusion system, which is a product into steam type. The product is sprayed into the top of a chamber filled with steam. As it falls, it condenses the steam, reaching the target temperature by the time it reaches the bottom. There are different distribution methods for the product. In method A, the product flows into a hemispherical bowl with a loose disc, forming a thin umbrella-like film exposed to steam on both sides. In method B, the product flows into horizontal tubes with slits, falling as thin laminar films. A diagram shows the infusion chamber with product entering at the top, steam inlets, and sterilized milk collecting at the bottom. A UHT process using direct steam infusion with a tubular heat exchanger includes a balance tank, feed pump, tubular preheater, steam infusion head, holding tube, vacuum vessel, vacuum pump, centrifugal pump, aseptic homogenizer, tubular cooler, aseptic tank, and aseptic filling. Finally, let's compare direct and indirect heating systems. Direct heating offers a very high rate of heating and cooling, is ideal for short times, can handle viscous products, is free from fouling, and can operate for long hours. Indirect heating has slower heating and cooling rates due to the physical barrier, longer come-up and cooling times, struggles with viscous products, suffers from fouling, and has shorter run times. In terms of cost, direct heating systems are more expensive due to special fabrication and design. They have higher operating costs because regeneration is lower, around 60%. They require more pumps and complex controls. There is also a risk of contamination in parts under low pressure after sterilization. Indirect heating uses standard, cheaper components like pipes, allows for high regeneration up to 90%, often uses a single product pump, and has no low pressure contamination risk. Thank you for joining this comprehensive session on UHT processing and aseptic systems. Understanding the differences between direct and indirect heating is crucial for selecting the right technology for producing high-quality, shelf-stable dairy products.